In the present lesson, we will be studying about semiconductor devices and in particular about the way a transistor can be used. The utility of the semiconductor devices is they save us a lot of energy. They are low energy devices. They consume extremely small amount of electric power. The miniaturization is another characteristic and which leads to reduction in size of the microprocessor or the semiconductor devices. These semiconductor devices, they have long life, that is they are very rugged. These are the three essential characteristics or utilities of semiconductor devices. They save us a lot of energy. They have helped us reduce the size of the electronic devices and they have long life. Historically speaking, the transistor was first invented by J. Bardeen and W. Brattain as point contact transistor, and also by William Shockley in 1951 as back-to-back junction transistor, wherein two p-n junctions were joined back to back. There are two types of transistors, PNP transistor and NPN transistor, and as you can see, the PNP transistor has a thin N region sandwiched between two P regions, and an NPN transistor has a thin P region between two N-type regions. If we take one of the two transistors, say NPN transistors, the central P region, that is the thin P-type part, is called the base and it has a very low doping level. It has two N-type uh, crystals. N-type, one of the two N-types is called emitter and the other is called collector. The different regions of a transistor, they have different doping levels. The three regions, as stated earlier, they are called the emitter, the base and the collector. These regions, they have different doping levels, as we'll see shortly. The emitter has moderate size, neither very small nor very large. It is however heavily doped. It has a high impurity level and it acts as source of large number of majority charge carriers. For example, in NPN transistor, the emitter is N-type and it provides the majority charge carriers, that is the electrons. The central region, the base, is small in size or it is very thin. It is lightly doped and the function of the base is to control the number of majority charge carriers flowing from emitter to the collector. That is, by applying suitable potential to the base, we can increase or decrease the number of charge carriers crossing from the emitter towards the collector. The third region, the collector, is always larger than the emitter. The collector is moderately doped, higher than the base but lower than the collector. It collects large number of majority charge carriers coming from the emitter towards the collector through the base, justifying its name as the collector. The circuit symbols of the two types of transistors are in this diagram. You have NPN. Here the emitter is always represented by an arrow mark. The central region is the base and the third terminal is the collector. Similarly, in PNP, you have this arrow mark on the emitter. The central region is the base and this terminal is the collector. As you can see, in NPN transistor the arrow is pointing outwards and in PNP the arrow is pointing inwards. In fact, the arrow gives the direction of the current because in NPN transistor the electrons flow from emitter towards the base into the transistor, and therefore the conventional direction of current is out of the emitter, hence the arrow is outwards. In order to remember, that is aid to memory of the symbols, is NPN never points in, that is the arrow is outwards on the emitter. To recap what we have studied so far, let's recall the differences between the emitter and the collector, that is their relative sizes. As we have studied, emitter has a smaller size or moderate size, the collector has a larger size. The base region is thin and low doped because the function of the base is to control the number of majority charge carriers from the emitter towards the collector without stopping any appreciable number of the charge carriers. Remember how in order to study the transistor action, we must recall what is a PN junction, which you have studied earlier, what is depletion zone in a semiconductor in a PN junction, what's forward biasing, and what is the reverse biasing, and action of the PN junction when it is subjected to forward biasing and reverse biasing. You will do well to revisit all these uh, terms, the PN junction, the depletion zone, the forward biasing and the reverse biasing, in order to understand the transistor action. Remember, a transistor consists of two PN junctions joined back to back. The charge carriers move across different regions when appropriate voltages are applied to them. Now, see this diagram. In this diagram, let's not apply any potential to the base. That is, we take base potential to be 0. Further, we have the emitter negative with respect to the collector. Now, let's probe this diagram and answer a few questions in the next slide. For your reference, the diagram is redrawn here. First question is, what type of biasing does emitter base junction have? If you look at this emitter base junction, emitter is N type and base is P type. With the emitter connected to negative terminal of the battery, emitter base junction is forward biased. Can this conduct in this biasing? Yes, the emitter base junction being forward biased can allow the current to pass. But in the diagram, we have the base collector junction reverse biased because the collector is N type and connected to positive. So the biasing given to BAC junction or base collector junction is reverse and it cannot conduct in this biasing. So overall, the transistor will not conduct in this biasing. Again, for the same NPN transistor, take base potential 0 but make emitter positive with respect to the collector, as you can see in the diagram. And we have the same 4 questions to answer. Let's go to the next part of the slideshow. Here, the biasing to the emitter base junction. Emitter base junction. Emitter is N type connected to positive. Therefore, emitter base junction is reverse biased, hence it cannot conduct. However, the base collector junction is forward biased because this N region is connected to negative, and the base collector junction being forward biased, it can conduct. However, the circuit is discontinuous at the emitter base junction due to reverse biasing, therefore the transistor will not conduct. So either case we have seen whether the emitter is negative or positive with respect to collector, one of the two junctions in the transistor is reverse biased and hence the transistor does not conduct. So for transistor action we need a different biasing arrangement, as you can see. Now in this biasing arrangement we have a separate battery for emitter base junction. The potential difference applied, as you can see, is VEB, potential to the emitter base junction. Likewise, we have the potential VEC, the potential difference across emitter collector. This is a circuit in which emitter is common and is connected to both base and collector. We call it a common emitter type of connection in the transistor, or the transistor is in common emitter mode. Let's see how the transistor will behave with such type of biasing arrangement. The arrangement is shown in the next slide again. What is the nature of majority charge carriers in the emitter? Here you can see the emitter is N type, so the majority charge carriers in emitter is negative, that is the electrons. The effect of emitter base potential on these carrier is, because the base is positive, so the electrons from the emitter they will be pulled towards the base. Since the base is thin and it has low doping, the electrons accelerated from emitter towards the base. They will not get enough holes in the base region for recombination. So only a very small fraction, say 1 to 5% of the electrons rushing from the emitter towards the base, they are lost in recombination with the holes in the base region. Most of the electrons, that is over 95%, cross over to the collector, which is reverse biased, that is it is at positive potential and hence it is capable of collecting those electrons. Further, if you increase emitter base potential slightly, that is base is made more positive as compared to the emitter, how does it affect the charge carriers and the collector current? The base will be capable of attracting much larger number of electrons from the emitter. However, it will not be able to stop them because of the low thickness and low doping level. Hence, an increase in emitter base potential results in a large increase in collector current. Similarly, if you decrease emitter base potential, the base will be collecting a smaller number of electrons from the emitter and hence the collector current or IC will show a sharp decrease. If you probe it slightly further, this you can see here. If we take VEB, that is emitter base potential, less than the barrier potential of this emitter base junction, we know that the PN junction does not conduct in such a situation and hence the collector current will drop to 0 or the transistor will become off. And if emitter base potential is large enough, then the transistor acts as almost conductor. Hence, there are two applications of the transistor which are very clear from this discussion. It can be used as a switch. It is off when the emitter base potential falls below barrier potential, and it is on when emitter base potential exceeds the barrier potential. The transistor also acts as an amplifier. The transistor also acts as an amplifier because a small variation in emitter base current, emitter base potential produces a large increase in the collector current. You may visit the website www.physicsbeckons.com for more topics. Thanks for watching this slideshow.